In the last tape, we started with vectors in 2 space and extended it to vectors in n space. In today's tape, we're going to be even more general. We're going to define the concept of vectors to anything that behaves like a vector. We're going to define a vector space to be any set of elements that satisfy the properties of vectors. And that would be the same properties of vectors that we established during the last tape. Let's let V be a set, any set, on which 2 operations, vector addition and scalar multiplication, are defined. If the following axioms are satisfied for every vector u, v, and w in V, and every scalar c and d in a set of real numbers, then V is called a vector space. So if I have a set of elements that has the operation of vector addition and scalar multiplication defined, and the properties of vectors are true for the elements within the set, then the set is called a vector space. Let's go back over the axioms. Now these are the same axioms that we had for vectors, the 10 axioms. The first is u plus v is in the set V. All that means is that set V is closed with respect to vector addition. So if u is a vector and v is a vector, then the sum u plus v is in the vector space. The commutative property of vector addition, u plus v is v plus u. The associative property of vector addition, I can change the grouping. Rather than grouping v and w, I can group u and v. We have the identity element, so that u plus the identity element is equal to u. So any vector u plus the identity element is equal to u. Also, we must have an inverse element, so that u plus the inverse element is 0. This says that scalar multiplication is closed. C times u is in V, so if u is in V, then C times u, scalar multiplication, is also in the set V. This is the distributive property of scalar multiplication over vector addition. C times u plus v is cu plus cv. Here's the distributive property of multiplication over scalar addition. Here's the type associative property of scalar multiplication. If I have vector u times scalar d times c, that would be the same as multiplying the 2 scalars, c, d, and then multiplying by the vector u. And finally, 1 times u is u, 1 being the identity, multiplicative identity vector. So any set of elements that has vector addition and scalar multiplication defined in such a way that all 10 of these properties are true is a vector space. So we're defining vector spaces based upon what the elements do, how the elements behave. We don't really care what the elements are. We only worry about how they behave. Let's look at an example. let's show that the set of all 2 by 2 matrices, that really should be M sub 2, 2. Let's show that the set of all 2 by 2 matrices, along with matrix addition and scalar multiplication, is a vector space. Well, we must show that all 10 properties are satisfied. Well, the first property. Well, before we start, we'll let U equal to the matrix U11, U12, U21, U22. V equal to the matrix V11, V12, V21, V22, and W equal to the matrix W11, W12, W21, W22. And we'll let C and D be real numbers. Well, the first property is closure. So we have to show that U plus V is an element of M22. Well, U plus V is going to be U11, U12, U21, U22, plus V11, V12, V21, V22, which by matrix addition is U11 plus V11, U12 plus V12, U21 plus V21, U22 plus V22, which is a 2 by 2 matrix. So I can just say this is an element of the set of 2 by 2 matrix, because the matrix has 2 rows and 2 columns. Since we started with the real entries, if I add 2 real numbers, I get another real number, so all 4 of them are also real entries. So we've proved condition 1. Now let's look back. Conditions 2 and 3 are really properties of matrix addition. So if you look back to matrix addition, you'll see that we previously proved or discussed properties 2 and 3. So I'll simply write that 2 and 3 follow from the properties of matrix addition. Look back in your textbook and you'll see that they were indeed proved. So 2 and 3 follow from properties of matrix addition. Property 4. We must show that we have the additive identity matrix 0 such that U plus 0 is equal to U. Well, we'll just define the 0 vector, or the 0 matrix, to be the matrix 0, 0, 0, 0. So then, U plus 0 will be U11, U12, U21, U22, plus the matrix 0, 0, 0, 0. Well, obviously this is just U11, U12, U 21, U 22. Because U11 plus 0 is U11, U12 plus 0 is U12, and so forth. So this proves property 4. Okay, property 5, I must show there's something the opposite of U, such that U plus the opposite of U is equal to 0. So property 5, I can just show that U11, U12, U21, U22 plus the opposite of U11, U12, U21, U22 is equal to 0. Well, we can see that's the case because remember the U's are simply real numbers, real elements. So U11 plus the opposite of U11 is 0. A real number plus its opposite is 0. And I need to go ahead and put opposites with all these. So this is the vector U. This is going to be the vector opposite of U. So you can see that in all cases it adds to 0. So it does satisfy property 5. Property 6 says that the set is closed with respect to scalar multiplication. So let's look at C times U, which would be U11, U12, U21, U22. Well, by definition of scalar multiplication with a matrix, that's just going to be C, U11, C, U12, C, U21, C, U22, which is, again, a 2 by 2 matrix. So scalar multiplication is closed. All 7, 8, and 9 are matrix properties, and they've already been proven. So we've already proved previously that scalar multiplication is distributive over vector addition, and that vector multiplication is also we have the distributive property over scalar addition and the associative property with scalar multiplication. Those have already been proved. Property 10 says show that the scalar 1 times U is equal to U. Well, the scalar is 1 and U is going to be U11, U12, U21, U22. Well, by scalar multiplication, I multiply the scalar by each of the elements in the matrix. So it would be 1 times U11, 1 times U12, 1 times U21, 1 times U22, which is just U11, U12, U21, U22. So the scalar 1 times U is equal to vector U. Scalar 1 times U is equal to U. Obviously, there must be a lot of vector spaces, or we wouldn't be talking about them. The set of all real-valued continuous functions defined over R, along with function addition and scalar multiplication, is a vector space. Now I'm just making that note. I will have you recall what I mean by scalar, by function addition. F plus g of x is f of x plus g of x. There's function addition. And then f of c of x is c f of x. That is your scalar multiplication. And you can go through and you can convince yourself that all 10 properties are true for the continuous functions with vector addition and scalar multiplication defined in this way. Show that the set of all polynomial functions of degree 3 is not a vector space. Show that the set of all polynomial functions of degree 3 is not a vector space. So what we do, we must show that at least one of the 10 properties is not true for the set. We must show that at least one of the 10 properties is not true for the set. Well, since I don't know which one may or may not be, we just go through the list. We'll look at closure, for addition. Now remember, in order to prove something is not true, all I have to do is to find an example. So let's let the vector u be, and we want all polynomials function of degree 3 to be x cubed minus 2x squared plus x plus 1. V, vector v, will be the opposite of x cubed minus 3x squared. So then u plus v will be x cubed minus 2x squared plus x plus 1 plus the opposite of x cubed minus 3x squared. X cubed and an opposite of x cubed gives 0. So I'm going to have a negative 2x, well, negative 2x squared minus 3x squared is a negative 5x squared plus x plus 1, which is not a third degree polynomial function. So the closure property fails. So we proved that it's not a vector space. So the set of all polynomial functions of degree 3 is not a vector space because they're not closed. I can add two third degree polynomial functions and get a second degree polynomial function. show that the set S is equal to the set of all x, 3x, such that x is a real number, along with the standard operations in R2, this should be 2 space, is a vector space. Well, in order to do that, we've got to show all 10 properties. So we start with closure. Well, we'll let U be the vector U, 3U. See how it is? Set of all x, 3x, such x is a real number. So it's x, 3x is key. So if I let vector U would be U, 3U. V, we'll let be V, 3V. And W, we'll let be W, 3W. Well, with closure, U plus V is equal to U, 3U plus V, 3V, which is equal to U plus V, 3U plus 3V, which is U plus V, 3 times U plus V when I factor out 3. So therefore, it's closed. Because I get the same pattern. This would be like the pattern x, 3x. Just let U plus V be x. So I have x, 3x, and it fits the pattern. Property 2, I have to show that it's commutative, that U plus V is V plus U. U plus V is going to be U, 3U plus V, 3V, which is U plus V, 3U plus 3V. I can turn this around and write it as V plus U, 3V plus 3U, which is the same as V, 3V plus U, 3U, which is V plus U. Property 3 was the associative property of vector addition. Well, I'm going to let you run through that one. It's just like I did up here, except you just have to go through, write it in the component form, then change the parentheses, and then write it back. So it's the same type thing we've done before. So I'm just going to say similar to 2. For property 4, I've got to find an identity element, 0, such that U plus 0 is U. Well, we'll define 0 to be the ordered pair 0, 3 times 0, which is 0, 0. So 0, 0 satisfies the condition of x, 3x. So then the U vector, this will be the 0 vector, the U vector plus the 0 vector would equal to U, 3U plus 0, 0, which is U, 3U, which is the U vector. So U plus 0 is U. Property 6 is to show that we have closure with respect to scalar multiplication. So if I pick any C, Now I can say that CU is going to be C times U 3U, which is going to be CU 3 CU. When I multiply C times U, C times 3U would be 3CU. Well, this also satisfies, so I'm just put therefore closed, because this satisfies the pattern. Just let CU be X. So I have X, 3X, satisfies the pattern, so therefore property 6 is closed. Property 7, we've got to show that C times U plus V is equal to CU plus CV. So we start with C times U plus V, which would be C times U 3U plus V 3V, which is C times U plus V, 3U plus 3V, which is C times U plus V, C times 3U plus 3V. Now, since U and V and 3U and 3V are just real numbers, I can use the distributive property of real multiplication over addition to get CU plus CV, 3CU plus 3CV, Let me show you something that some people do. The next step here is really fairly obvious, but sometimes people get to a bind and can't make the connection. Well, what you can do, without really anyone seeing it once they read all the way through, is to go down to what you're trying to prove. Now, what I'm trying to prove is CU plus CV. So that's what I should end up with. Well, if I work back, this would be CU 3U plus CV 3V. Which this is going to be CU 3CU plus CV 3CV, which if I go up I get that step. So now when you look at the whole thing, you can't tell that I started up here and worked and then started and worked back up. So when you turn it into me, you want to make sure that it looks in a straight line. But when you're doing scratch on your paper, you can make the two ends meet as long as you've got a reason for everything, and that helps you go back and see what you've done. Okay, now properties 8 and 9, I'm going to leave those to you by just saying 8 and 9 would be similar to 7. So the proofs of 8 and 9 are similar to 7. And I even let you do this on the homework. You show me as you're doing your homework and you're proving that something's a vector space. If you can look through in your head and see that it's just the same type of operations, and you tell me they're similar, then I'll let you buy with it, provided that you do enough of them for me to know that you understand it. Okay, so let's look at 10. We need to show that 1 times u is u. In other words, the scalar 1 times u would be u, or that would be 1 times u 3u, which is obviously u 3u. So we've proved or discussed all 10 properties. All 10 properties are true for the set of all x 3x, such that x is a real number. So therefore, the set of all ordered pairs x 3x forms a vector space with the standard operations of vector addition and scalar multiplication.